In this chapter, we transition from using statistics to describe data to using statistics to make inferences from data. Inferential statistics allows us to draw conclusions about our dataset, even when we don't have all of the information. It is a common scenario that we won't have complete datasets to work with, and the techniques within inferential statistics allow us to use these subsets of data and make predictions, or inferences, about the entire dataset. We will start the chapter with a review of the key concept of inferential statistics: populations and samples. Then we will go through a scenario that will help us introduce some important methods needed to implement inferential statistics: p-values, alphas, confidence levels, and how we interpret the results of a statistical test. We will wrap up the chapter by going over important concepts when it comes to applying inferential statistics, what to keep in mind when we pull samples from our data. This includes how we can determine the necessary sample size for our analysis, as well as the law of large numbers and the central limit theorem. But more importantly, why these matter to us when we are using inferential statistics. Through this chapter, we are going to have to grapple with some terminology that may be new to you. Frequentists tend to be very careful and very specific with their terminology, and some of it might seem a little unintuitive at first. For that reason, we're going to take our time to explore these ideas, and we'll include a number of exercises and explanations to ensure we're really comfortable with this critical terminology and concepts by the end of this chapter. The topic of populations and samples are key to inferential statistics. In the first chapter, we discussed the difference between populations and samples. In inferential statistics, the sample is a set of observations of the population used in our analysis. The population is what we want to analyze and understand more, and the population can be items, events, or people, with a common feature that we have questions about. This could be any definable group of people, places, events, or things: customer returns, home foreclosures, European automobile companies, sports fan demographics, wind farms, really any set of data. Samples are taken from a population for analysis because it can be too time-consuming, costly, or even impossible to capture all of the observations from an entire population. Therefore, samples are taken and analyzed. Insights that we derive from these samples may help us make inferences about the larger population that they were taken from. Usually, if the samples are random and large enough, they are representative. However, samples can also occasionally mislead us. That's just the nature of randomness of taking samples from a population. After we take samples from our population, we usually run experiments and tests on these samples to derive insights, so that we can make inferences about the population. P-values are an important concept because they can help us measure the significance of the results of our experiments. Let's explore the concept of p-values by continuing with our tree scenario. On average, without any intervention, our trees have a survival rate of 67%. We've been researching ways to improve this and want to test the effects of two separate fertilizers. Fertilizer A and fertilizer B are both supposed to improve the survival rate of our trees. However, we believe that these two fertilizers will have a different effect on their survival rate. This is our starting hypothesis, but let's run a few experiments to see if this hypothesis is true. For the first experiment, we give one tree sapling fertilizer A and another tree sapling fertilizer B. At the end of 1 year, the sapling that received fertilizer A is alive and healthy. The sapling that received fertilizer B is dead. Our original hypothesis was that the fertilizers would produce different results. Can we confirm this based on the results of this one experiment? Or should we reject this idea and conclude that fertilizer A is no different from B? Well, we can't really draw any conclusions at this point. There are a lot of reasons why the second tree might have died that have nothing to do with the fertilizer. Genetics, disease, maybe the fertilizer wasn't applied properly, or perhaps just random chance. Either way, we need to use a bigger sample in our experiment to draw a meaningful conclusion. In our second experiment, we have 6 trees in each group. 5 trees in Group A survived, a survival rate of 83.3%, while only 2 trees in Group B survived, a survival rate of 33%. Remember, our original hypothesis was that the fertilizers were different. Can we confirm this hypothesis now, based on the results of the second experiment? Or should we reject this idea and conclude that fertilizer A is no different from B? Again, it's very hard to say based on the results of this experiment. Maybe the fertilizer wasn't applied properly in a couple of cases, and it just so happened to be that those cases were both in Group B. Or maybe these particular trees both had some genetic problem. Or maybe something about these trees, besides the fertilizer, helped them live. Again, for us to have confidence in our results, we need a bigger sample. In experiment 3, we have 1,000 trees in each group. For fertilizer A, 900 trees survived, experiencing a survival rate of 90%. With fertilizer B, 800 trees survived. This means they experienced an 80% survival rate. Again, can we confirm now that fertilizer A has a different and likely better effect than fertilizer B? Or can we conclude that fertilizer A is no different from B? At this point, yes, we could be fairly certain that they are different. It would seem unrealistic that these results were just due to random chance. Sure, there might be some randomness and some other factors going on, but the results seem clear. Finally, let's run our last experiment. In experiment 4, we again have 1,000 trees for each fertilizer. Fertilizer A now has a survival rate of 74%, while B has a survival rate of 69%. So, could we in this case confirm that fertilizer A is different from B, or should we reject that idea? This is starting to get a bit tricky, and it's at this point that we need our p-value to help us. A p-value can measure the significance of the differences that we're seeing in each of the 4 experiments, and we can use this p-value measure to conclude whether the differences occur by chance or occur because of an underlying effect of the fertilizer. Our p-value says, assuming that there is no difference between the effects of the fertilizers, what is the probability of observing the differences in our experiments, as extreme as they were, purely by chance? In the first scenario, our p-value was 0.16, so assuming that fertilizer A and B were in fact the same, there's a high probability that we could observe our results by chance. In the second, our p-value was 0.08, so assuming fertilizer A and B were the same, there's still a reasonably high chance of observing these results purely by chance. In the third, our p-value was very small. There was a very low probability, 1 in 2.5 billion, of observing these results by chance. Our p-value was 0, decimal, followed by 9 zeros, and then 4. And in our fourth experiment, our p-value tells us that, assuming A and B were the same, we'd have a 0.013, or a 1.3% probability of observing these results by chance. So again, if these results are so unlikely, perhaps we should reject the idea that A and B are the same. Put differently, this p-value tells us that if there was no difference between fertilizer A and fertilizer B, we'd expect to see results this extreme about 1.3% of the time. Overall, we can see that the smaller our p-value is, the more confident we can be that fertilizer A is different from fertilizer B, due to a reason other than chance. We've just seen what p-values are, and how they can help us measure the significance of the results of our experiments. But how exactly do we calculate a p-value? Let's use a simple coin flip experiment to demonstrate the calculation. Doing this will help us better understand what the p-value means. Consider the following. My friend gave me a coin. which I believe is totally normal. I have no reason to believe that the coin is unfairly weighted in any way. So let's use this as our starting hypothesis and see if our coin flips can support our belief. I start flipping the coin, and after 5 flips, 4 of them result in tails. Now this seems like an interesting result. Does our initial hypothesis hold up? Is the coin normal? Or perhaps our initial thought was incorrect, and the coin is actually special, or maybe it's weighted in some way. To answer this, we could think about the question another way. If our coin is totally normal, how unusual would it be to see results as extreme as this? Our p-value tries to communicate exactly this probability. We get our p-value by adding together 3 different parts. The first is the probability of our observation given random chance. The second is the probability of observing something equally as rare. And finally, the probability of observing something even more rare. If we add these 3 probabilities together, we get our p-value. So let's start with the first part. When we flip a coin 5 times, there are 32 possible outcomes. There are only 2 possible results of a single flip, heads or tails, and we get these results 5 times after 5 flips. So 2 times 2 times 2 times 2 times 2 is equal to 32. 5 of these outcomes look like our result of 4 tails and 1 head. Note that we don't care about the order in which we get our tails and heads from our coin flip. So for the first part of our p-value calculation, we can add 5 and 32. It would be equally as rare if we observed 4 heads and 1 tail. So for the second part, we need to add that into our equation. That gives us another 5 and 32. Finally, we need to add in the probability of observing something even more rare. There are 2 such outcomes, 5 heads in a row and 5 tails in a row. So we'll add 2 and 32. This gives us a total of 12 and 32, or 0.375. So, if our coin is normal, we can expect to see results as unusual or more unusual than this about 37.5% of the time, which is a lot. And so, what we can say is that there's very little evidence that our coin is anything other than fair. Now that we've explored the concept of p-values in a little bit more detail, the next question we need to answer is, how small does our p-value need to be for us to be confident in our results? In other words, what is a threshold that we can set for our p-value so that we can be confident in whether our original belief is true or not true? For our trees, how small does our p-value need to be for us to be confident that fertilizer A is different from fertilizer B? In our 4th fertilizer experiment, we had a p-value of 1.3%, or 0.013. This told us that it was unlikely that fertilizer A was the same as fertilizer B, but it didn't say that it was impossible. So, if we choose to reject our original belief, there is a small chance that we're making the wrong decision, but we have to draw the line or add a threshold somewhere. This threshold is known as the alpha, and if our p-value is lower than our alpha, we can be confident in our results. Commonly used alphas are 0.10, 0.05, and 0.01. For our 4th fertilizer experiment, if we choose an alpha of 0.05, our p-value would be less than this, and we can conclude that fertilizer A is not the same as fertilizer B. A related concept to alpha is the confidence level. The confidence level is calculated as 1 minus the alpha. If we choose an alpha of 0.05 for our fertilizer test, this means our confidence level is 95%. In other words, an alpha of 0.05 means that the conclusions we draw from our experiment are correct 95% of the time. On the other hand, this means we have a 5% chance of our conclusions being incorrect. The reason this happens is that our experiments were run on a sample of trees from our population. Most of the time, our sample is representative of the true population distribution, but occasionally it isn't. To summarize, the alpha sets the threshold at which we measure our p-value against. If our p-value is lower than our alpha, we can accept our results. The confidence level is the probability of our results being correct. It is calculated as 1 minus the alpha. An alpha of 0.05 will result in a confidence level of 95%. As we progressed through our tree scenario, we ran a few experiments that compared the survival rates of trees that were given either fertilizer A or fertilizer B. As we went through the scenario, we explored the concepts of a p-value, alpha, and confidence level, and how they help us measure the significance of the results of our experiments. But let's take a step back and revisit our initial hypothesis. Fertilizer A and fertilizer B are both supposed to improve the survival rates of our trees. However, we believe that these two fertilizers will have a different effect on their survival rates. With this in mind, recall what our p-value states. Assuming that the effect of both fertilizers are indeed the same, what is the probability of observing the differences in our experiments, as extreme as they were, purely by chance? Notice that we are not trying to prove our hypothesis with our experiments. Essentially, we are trying to disprove the thought that the effects of the fertilizers are the same. To do that, we try to show that it's absurd to think that the effects of the two fertilizers are the same. This is an act of reductio ad absurdum. We are trying to make the claim that these groups are different by showing that the opposite scenario, that they're the same, is absurd. The trick here is that it's often easier to show a statement to be false than to prove that it's true. For example, consider the statement, "all swans are white." To prove this, we'd need to examine all of the swans in the world. However, to disprove the statement, we would have to observe only one swan that is not white, like a black swan. With this single observation, we can show the statement, "all swans are white," is wrong, and we can reject it. To use a quote often attributed to Albert Einstein, "No amount of experimentation can ever prove me right, but a single experiment can prove me wrong." So instead of trying to prove how different our groups of fertilizers were, we just try to reject the idea that they are the same. We'll come back to this concept when we run our hypothesis test in the next chapter.